Okay, so this is the same problem or a similar problem like the previous one, but here we approaching the problem with different method. We're using the classical method to solve, and this method it's good to avoid doing convolution. So our goal is again to find the loop current as our output. We are given an input, but we don't have the system, so we need the system. Then we can take the input and the system and do convolution like the previous one. But however, this problem, we can approach it here easily using the classical method, since we have the input in exponential function into u of t. So this is what we're supposed to do. First, we write the differential equation that describes the circuit. So we start here with using a KVL, input voltage equals the voltage drop from the inductor, resistor, and capacitor. So again, from here, you can replace this integral by taking second derivative. So take derivative both sides. If you take the derivative both sides, that will end up with second derivative here, first derivative here, and the derivative will cancel the integral, and then you get back to the original function. So we can transfer now this equation from using Laplace transform into our S domain. So now d x of t, the transfer is s x of s, and now this one, since we assuming that the initial conditions are 0, so we have s squared plus 3s plus 2 y of s, and we know our h of s is y of s over x of s. So here, this is our transfer function. The previous one, we get the transfer function into s domain, and then we took the inverse to find h of t, and then we took h of t convolution with the input. So input convolution with h of t, the system gives us the output. However, we can just stop right here in this method. Once we have our h of s, we take this h of s and we use it to solve for the forced response. So this our here, look at here, our output is the summation of the natural response plus the forced response. So this part is important to get our forced response. However, our natural response is easy because you can just assume this is a homogeneous differential equation, and you can just factor this polynomial, set it equal to 0, factor it, and then you can find our natural response as this here, c1 e to the minus t plus c2 e to the minus 2t. This is how we find the natural response. And this one now is helpful in this case to find the forced response. How we find the forced response? We take the transfer function that we got right here, we multiply it by the input function, and then what we do, if we did that, this is how we calculate it. So you have the transfer function multiplied by the input function that you have, and this here, this number represents the s value. So this s is equal to this number, so s is equal to -3. You plug in here, and finally you find your forced response. So this is your forced response. Once you have the forced response, your total response is the summation of the natural plus the forced. So you have the natural already by solving the homogeneous differential equation from this side of the equation, and from the other side of the equation you get the forced response by applying this classical method if you have an exponential function as your input and y of t. And this is how we finalize this equation. So this is our output, loop current is equal to the summation of the natural plus forced response into u of t. And you can solve using the initial condition that's given here, those initial conditions, to just find those constants c1 and c2. So this problem is much easier if you approach it using this classical method when the input is given into exponential function u of t, and then this is what you're supposed to do. First, you drive the equation, you put the differential equation, you find the transform, S domain, you find h of s, you take h of s to calculate the forced response by multiplying the h of s by the input that you have, and then the natural response, you just have it from this side of the equation by factoring and find the zeros. This is how you find your natural, and then plus the forced that we get from here. This is your total response, and instead of doing convolution like the previous problem.